getting involved in databases back in the 80s when I was asked to port Ingress to IRIX 6.5. At that point, the best recommendations for how do you set up a database is to set them up directly on the raw partitions. Put your log file on a separate disk and only use the outer segments where it's fastest, and stripe all your rest of your table space across as many spindles as you can find to try and get speed. And don't let any of the operating systems, buffer cache, or file systems to get in the way between your database engine and your disks. So that was the recommendation. But let's look at a typical storage stack today. It looks something like this. This is simplified. At the bottom, you've got your disks. And disks do all sorts of weird and wonderful things inside. And they remap your requests, so you don't know whether, if you take this block, then that block, whether they're actually going to be contiguous on the disk or not. You don't even know whether it's going to be the same unit, because an SSD could have lots of different flash cards and it stripes things internally, it's RAID internally. You've got no idea of the topology inside your disk. And on top of that, we put a RAID controller. That may or may not export the topology of the underlying system to the next layer up. And then if you're a systems administrator for an enterprise class machine, you're probably using a logical volume manager on top of that, which again hides the topology of the things. So it creates volumes that may or may not be striped over multiple RAID arrays, may or may not have caches involved with a SSD in there somewhere. And then you've got the page cache or the buffer pool, which I've put in as a layer, but it isn't really, it's sort of off to the side. And then you've got your file systems on top of that, and a VFS on top of that, and then a system call layer, and you put your database management right at the top, and it doesn't know what the topology is anymore. So the user space doesn't understand the disk layout, and it can't optimize for it. That could be a good thing. I mean, maybe the kernel knows better than the user space how to optimize stuff. But database management, I don't know. And file systems also can't see the disk layout, and XFS in particular really wants to know how the disks are divided up so it can optimize parallelism at the lowest level. So let's try turning it upside down. Let's put a relational database management system right at the bottom, directly on the disks, which is as close as we can get to the hardware. Put Fuse or something on the top because database managers want to talk to user space. They don't want to talk to the kernel. And Fuse lets you put a file system in user space. And then we can have all those other things on top, and let's see what's going on. I've wanted to do that for ages. If you think about what a file system actually is, it's a set of mappings. It's a mapping from a name to a set of metadata, all the ownership and file modes and all that stuff that you do when you do an LSHL. And it's a mapping from name to file content. In POSIX-related systems, we don't have any funky file systems that do index sequential access method or anything like that. That's assumed to be done at user space. The other place that you've got a mapping is from name to name for symbolic links. So a symbolic link is just a mapping from a name to a name. When we've got this in the file system, we want to order the writes for consistency. So you want to make sure that you do things in the right order. So if you get a crash, your file system can still be understood. The on-disk layout can still be understood by the file system when it comes up again. We want to make sure that writes to different files are isolated from each other. So that if I write to this file, it doesn't interfere with the writes to this file. And if possible, your file system should even make the performance not noticeable. So if you've got heavy write on this file, it shouldn't really affect the speed of writes to this other file. And a good file system will spread things across the spindles it's got, so you do actually get some of that isolation. And the other thing you really want from a file system is that if you call fsync on an open file, when that fsync returns, you know that if there's a crash, the data is actually on permanent storage and you can get it back. I've had some file system implementations where that's not true, and it's a bit annoying. Now, if you think about this, this is exactly the standard ACID properties that a database has got, with the addition of atomicity. Some file system operations have to be atomic. Creating a link, doing a rename, you expect those to be atomic. And there's a few others too. But the other ones, the ones we just talked about, they're just the ACID things. So let's use a relational database management system that handles replication, perhaps, at the bottom level. This makes it really easy to add new attributes. So maybe we want to use an Apple-like file system with a resource fork, or maybe we want to try funky ACL mechanisms. And you can do that very easily. And because the database engine guarantees consistency, maybe we can throw away the need for FSCK ever. And if we use a relational database system that handles replication, for example, MariaDB with Galera, then we can get distribution for all those free. But, there's a big but here. Most of the modern relational database management systems we've got, such as Postgres, rely on aspects of the file system for their operation. They don't run on raw disks anymore. At least Postgres does. I discovered only last night, by talking to one of the MySQL maintainers, who happens to be at the conference, that MySQL you can actually configure to do on raw disks. But because I only found that out last night, I haven't tried it yet. Anyway, I've been looking to do this for ages, but haven't had time. One of the things our group does, we have a research group at a university, is every year we invite good students to come and spend the summer months with us embedded in the research group. And this year, Sam Lee turned up and wanted to do this task. So he started looking at what it would take to put a relational database level, what table schemas you'd need, what queries you'd need to be able to do the stuff. But while he was doing preliminary work, he discovered that it's already been done. This sounded like it was going to be a really short project. Mr. Tsukasa Hamano from Japan and Mikael Ludwig, who's from somewhere up north, but currently lives in Southeast Asia, created a thing called MySQL-FS back in the early 2000s. It hasn't been touched since 2009, which means it doesn't compile with GCC version 8 anymore. That was fairly easy to fix. What it looks like is this. This is the schema. You've got 3 tables. The tree table, which maps inode to parent inode to name. So it's indexed on name, and it's indexed on inode. So you can do a search on the inode to find the name, and you can do a search on the name to find the inode. That already gives you something that's better than most file systems, because you can't actually look up a name from an inode very easily. And by joining on inode to parent, you can get everything that's in a directory. You've got the inodes table, which contains all the metadata except for the number of links that a file has. That gives you the modified time, the creation time, the mode, and 2 extra things, whether the inode's in use at the moment and whether it's been deleted. Because this file system doesn't track nlinks, you need to have a separate flag to say that it's been deleted. You can't delete things straight away because they might be in use. When in use goes false and deleted goes false, then the inode can be removed. And finally, you've got the data blocks. Data blocks is just yet another table with 4K blobs in it and a sequence number. The sequence number is the sequence number of the 4K blob in the file's extent. So the first 4K's got a sequence number of 0, the next one's got a sequence number of 1, and so on, and which inode it's in. And that's all you need to implement a file system. Looks pretty nice, doesn't it? When you want to actually do a lookup, let's say I've got a name and I want to convert that to an inode and all its status. You get this really funky query. It's a self-join on the parent inodes where you match the names to the parents. And you can do that in one query and get all the results you want. You know, there's a subquery in the middle there to count the number of links, so you can get n links at the same time. This ends up being quite expensive. If you get rid of that, you double the speed of the query. But we'll come to that later too. So we've got this thing. Out of the box, and this was about 3 weeks ago, we got this working. It sort of passes the POSIX test suite, except CTime updates to directories don't happen. And if you look at the way that the schemas work, that makes sense. Because to update a directory, to add a new link, all you have to do is enter something into the tree table. And it doesn't touch the inode table at all. So the ctime doesn't get updated. In fact, ctime almost never gets updated. But that was some bugs. Rename integrity checks. Finding out whether a directory is empty or not, or even whether an inode is a directory or a file, is an expensive check because you have to look at the inode table, not just the tree table. Which meant that when you do a rename over a non-empty directory, it does the rename quite happily, and all of the files that were in that directory become orphans. Yeah. And multi-user mounts. It turned out that the version of Fuse that was being used only hoped single user. So if you tried to access the file system as somebody who wasn't the person who mounted it, it would give you all sorts of weird error messages that didn't match the POSIX standard for the system calls you happen to be doing. And that really confused the test suite, I can tell you. And yeah, long file names silently get truncated to 254 bytes. Not 255, 254 bytes. And if you've got a path name longer than 1024, it got truncated to 1023 bytes before it got past a name I, which meant that files seem to disappear sometimes. And. All right, what about performance? Can we actually get good performance with this? It was rather slow. This was on a slow disk, and it turned out to be mostly log file writing to that slow disk and MariaDB slowness. We didn't do any tuning, we just used everything out of the box. So let's get a faster disk. We'll put a machine in with an SSD. This is a bit better, 40 times slower than XFS for Postmark. Postmark, by the way, is a benchmark that creates, rewrites, and deletes lots and lots and lots of small files. It's meant to emulate a busy mail server running with a MailDir type backend. And, ooh. Okay, we've got to fix this. So, let's move first to from Fuse version 2 to Fuse version 3. The big difference between Fuse version 2 and Fuse version 3 is that a lot more operations, the inode number is cached in the Fuse layer. So instead of having to do a lookup and that funky join for every single system call, we could just use the cached version of the inode. That gets rid of an expensive query for almost every operation. Also, where we're already accessing the inode table, we'll add in the ctime and mtime updates. getAttra which is essentially stat, which is called for every directory lookup, and for an awful lot of times, things like Postmark are doing stat as well as open or close. And when you do a getDents call, a stat call is called internally to fill in the dentry buffer for each time you go through, so you can get both at the same time internally. So we can reduce the number of queries in getAttra by a factor of 2 because it was doing 2 sets of queries. The first one to get most of the attributes, and the second one to get the size with a separate query on the data blocks table. By caching that inside the inode, firstly, it meant that we had to do an update to the inode after a write, which meant we could update them on modified time. And secondly, it meant we didn't have to do another scan of the data blocks every time we did a stat to get the size. So that was pretty good. I fixed the rename problem, and Fuse version 3 has got 2 extra flags you can use when you set up the Fuse system. Allow user, which gives you multi-user, and use ino, which meant that we could get all this caching going properly. So that was a lot of work that we did. We've still got some non-POSIX semantics. dot and dot dot in every directory aren't really there. They're just added in when you could do the getDents call, which means that as they're not really there, they don't contribute to nlinks, which meant that you'll find optimizations that say anything that's only got 2 links must be an empty directory. Doesn't work. CTime's still not updated on directories, and directories always have 0 size because they don't have any content except in the tree table. And statvfs isn't implemented, really. There's also a fuse bug somewhere. Every now and then, if you use the fuse-mounted file system with this thing, and you type sync, it hangs. And the only way to fix that is to reboot the machine. But now, with all of this, we're only 9 times slower than XFS. And read and write's only 7 times slower than NFS, and about 10 times slower than XFS. But CPU utilization is 2.5 times higher, mostly in the database engine. To give you an idea, git clone on the Linux source tree, comparatively, on XFS it's real time of 9 minutes, 23 minutes on MySQLFS. But if you look at the user and system time, it's comparable. That's because the CPU time used by the database management system is much, much higher. And so that's where all the time's going. The worst offenders are create, rename, unlink, write, and stat, which are using getAttra internally and does all that funky joins in order to find all the nlinks. If we cache nlinks, we should be able to get faster. Also, we're doing 3 queries for every block written. We do 1 to see whether that block is already in the database, and if it's not, we insert it. Then 1 to update the contents of that, and then 1 to update the inodes, ctime, and size. We could probably get that down to 1 query per block written and 1 query per write, just by updating the size at the end instead of at the beginning, instead of for every block write, at the expense of loss of some atomicity. So that's more stuff that we can do. We could also cache the type and the mode, which are the only 2 bits of the inode that you actually need for getDents in the tree table. We can also cache recently used inodes and double the block size, which would reduce by half the number of queries. But there's all these new things that's possible too. We can use replication. That works. We tried it out. It does give you a slowdown. Because you've got to do a 3-phase commit as soon as you've got replication on the database, it adds the network delays plus the commit time for the remote disk onto whatever you're doing. So it does slow things down a lot. We can also do a fast find. Find over a file system at the moment has to do a recursive descent and match all the attributes. That just becomes a database query, and databases are really fast at that stuff. From a 5-minute query to scan and print out all the names, it becomes like a 0.1 second query to print out all the names if you just do it directly through SQL. If we add an index on the content, we can do full text searches. FACK, I said we didn't need it, but if you do need it, you can write one that's really fast. And it's easy to add other features like resource forms. You can get it at the moment from GitHub. Pull requests welcome. It more or less works. The performance isn't too painful. I think it's actually quite a useful platform for experimenting with other file system things. And it's also a good exercise in optimization techniques if you want to make it faster. And pull requests welcome. Okay, have you got any questions? Yep, at the back. Can we get a mic up there, please? There's one at the back in the middle.
I've got to ask this one. Have you then installed a database onto the
I would love to try that at some point, but I haven't done it yet.
Because I would be interested to see how poorly that performs.
Yes. I'd be interested to see whether the semantics are maintained all the way up and down. Other questions? There's one there.
Just why?
Because it's cool crack.
Yes. There wasn't a real reason, it was just a cool idea.
Yeah.
Have you tried looking at doing like sort of an inline blob for sort of small files? Because usually they're stored within the block of the row. So if you had like small things, especially for something like postmark, and I think it's up to 768 bytes for an ODB, can be stored inline. So it would be that one operation when you go and do the stat, you'd get the data.
I haven't done that optimization yet. It's a good idea. Pull requests welcome.
Have you considered a more traditional Filesystem model where you move the tree into the inode?
The problem with moving the tree into the inode is you lose the multi-way mapping from name to inode. So you can't have more than one link to a file then.
Is there any other database engine other than MySQL suitable for doing this? Would it be better, or is this deep in the MySQL engine?
We started with MySQL because we already had the code as a starting point. You could do it with any database. As it turns out, MySQL, you can talk directly to the hard disk, so that's going to be the next thing we try, because I'd like to get rid of the file system layer as part of the problem, perhaps. But yeah, give it a go. You can use anything with SQL at the moment. Any more? Okay, as I said, pull requests welcome, have fun.
We're going to have a